Our third type of conic section that we'll take a look at is the hyperbola. We'll save the parabolas for last. And so as you can see there, it's the one shape, the one cross-section that has two separate pieces to it, two separate branches as we refer to it. You can see the plane is vertical, it's parallel to the height of the two cones that are placed tip to tip. And so as we slice through, the cross-section shape that we get are these two branches that look kind of like parabolas, but are different, and they extend forever in both directions. So when we look at the equation of a hyperbola, you'll see it has a lot of the same elements that the circle and then the ellipse did as well. We've got the x minus h squared, we've got the y minus k squared. Just like with the ellipse, it's equal to 1. We have denominators a squared and b squared. But the key difference, especially that with the ellipse, that allows us to recognize it as being a hyperbola, is the fact that it's the subtraction of the two fractions as opposed to the addition. And so that comes out of the definition. If we go to the rule that establishes a hyperbola up above, there's only one word change from the definition of an ellipse and the definition of a hyperbola. But that one word difference makes a huge impact on what the shape ends up being. So it's a set of all points x, y. So we've got our points that are on the curve of the hyperbola, whether it's one branch or the other. And it's the set of points whose difference, the difference of whose distances from two foci is constant. Meaning that if I take, so if this is one focus here and this is the second, if I take this distance and I take this distance and I subtract them, or if I take a point over here and I take the distance from one focus and the distance from the other focus and subtract them, that difference is constant. So rather than adding those distances, it's subtracting those distances keeps on giving us the same number. And so as a result, we can end up with really, really large distances as long as they subtract to make the same number. Those points are going to be on the branches of the curve. And that's true for both sides. So we can have points that are along the lower branch here as well. And so just that one word difference, that change between the two definitions, gets us from having a closed shape like the ellipse to having this boundless set of two branches that is the hyperbola. So we still have some of these same features, however, between the two shapes. So I'm going to clear everything here just so that we've got a little bit cleaner display. So we still have h and k as the center of our shape, so that's going to be the halfway point between these two branches. The 2 points that are a away from the center are our vertices. So that's going to be right here and right here. Those are our 2 vertices. So those are actually the points that are closest to the center, as opposed to in the case of the ellipse, the vertices are the points that were the farthest away from the center. These 2 points here are our foci. So just like with the ellipse, we don't have the shape without the foci. If we look at the definition, that's really the only feature that's mentioned in the definition. But now the foci are farther from the center of the hyperbola as opposed to closer than the vertices as they were for the ellipse. And the key difference for determining the relationship between A, B, and C, and I'll talk about the role that B plays momentarily, the relationship is a squared plus b squared equals c squared. So it's more that kind of Pythagorean theorem equation that we're familiar with, not the a squared minus b squared equals c squared that we had with the ellipse. And so as a result, we can see that we're adding two things together to make the c squared. And so as a result, c is going to be the biggest of those numbers, and that's reflected by the fact that the foci are the points that are farther away from the center as opposed to the vertices, which are only a away from the center. The last thing that we haven't talked about is what role b in the equation place, the b squared. So they're not shown in these diagrams, but the branches of the hyperbola approach a set of asymptotes that intersect through the center of the ellipse. So we can imagine that we have these two lines that are intersecting at the center of the hyperbola, and as these branches of the hyperbola extend farther and farther in each direction, they are actually getting closer and closer to these two asymptotes that are crossing through the center. And so the question is, what are the slopes? What is the steepness of these asymptotes? And the way we determine it is by either taking a over b or b over a, throw a plus or minus because one is going up from left to right, one is going down from left to right, and that's going to determine the steepness of the lines. Now I'll be honest, I can never just remember outright which one is which. So for a horizontal transverse axis, meaning when the axis that contains all of the center vertices and foci is running horizontally, then it's supposed to be plus or minus b over a. When it's a vertical transverse axis, it's supposed to be plus or minus a over b. So in the circumstance here, where all those points are on the same vertical line, it's a over b. I'll be honest, I can never keep straight which one is supposed to be which, just thinking of it that way. But the way I do remember it is, unlike in the ellipse, where a squared was always the larger denominator and b squared was always the smaller denominator, for a hyperbola, we'll notice that a squared is always underneath the positive variable, so the one that's doing the subtracting in our equation. And b squared is always under the fraction that's being subtracted. So it's not size dependent. A squared can be smaller than b squared in a hyperbola. And so the way I remember whether it's supposed to be b over a or a over b is, instead I say whatever number, the square root of which is underneath the y, since is going to be in the numerator of my asymptote fraction, slope fraction, and whatever variable, whatever number is underneath the x is going to be in the denominator of my asymptote slope fraction. And so I think of that as like a rise over run. We know that's how we determine the slope, so that's the change in y over the change in x. So I just remind myself that I'm going to stay with that idea. I'm going to go with the y over x to figure out my slope. So I'm going to go with the y denominator over the x denominator to figure out the slopes of the asymptotes. And then the one thing that we do have to remember is it's a over b or b over a. It's not a squared over b squared or b squared over a squared. So we just have to remember to take the square roots of those denominators when setting up our slope fraction. So again, a lot of information here kind of thrown at us. I think hopefully things will come into a little bit more clarity as we start to go through some examples of how we can take an equation and piece together the graph and all the relevant features in the next video.